My name is John Bullivant. I'm the chairman of the technical committee for the 16th Electrical and Electronic Insulation Conference being held in Chicago. During the course of the conference, we try and select papers which we feel will be of considerable interest to not only those people at the conference, but to other people unable to attend it. Mr. Jim Timperly presented a paper entitled Detection of Insulation Deterioration Through Electrical Spectrum Analysis. And in the course of this presentation, it produced a considerable amount of discussion from the people attending it. On this basis, we feel it will be of interest to a wider audience, and therefore it is a pleasure to present to you Mr. Jim Timperly.
Even though modern machines are usually well designed and operated far below the manufacturer's design limits, failures can occur, either in the slot section or in the end windings, depending on the particular failure mode that's involved. In particular, several types of faults can be identified through measuring them by monitoring the radio frequency current at the neutral. In particular, we'll be talking about electromagnetic interference, or EMI, its measurement, its identification, and if considered serious enough, the elimination of EMI through maintenance procedures. EMI is common to all machines. It can cover an extremely broad spectrum of frequencies. In a particular hydroelectric machine, this was from 6 kilohertz to 220 megahertz. Similar machines, that is those with similar stator designs, produce a similar spectra of EMI. One of the nice features about this type of testing is that early incipient fault detection is possible. EMI does tend to increase as deterioration increases, and likewise EMI is stable if the defect is stable. And most importantly, certain types of EMI are produced by defects only at certain frequencies. To show you one of the various types of EMI, this one is called microsparking. The photograph in the upper part of the slide shows the extremely rigid pattern that's produced both on positive and negative half cycles of the power frequency. This can occur in machines at very discrete frequencies. For example, at 23.5 megahertz, we had a quite rigid pattern. This makes a popping sound due to microsparking, or that is discharges across very small gaps. If one would tune to, say, 22 megahertz or 25 megahertz, this pattern would be completely gone. Another type of EMI is corona discharges, usually on the surface of the stator coils or stator bars. It's an extremely random pattern. One can see the, in this case, 60 hertz power frequency hidden within all of the random corona noise. It makes a hissing sound or sound somewhat like bacon frying. Both can occur at the same time, as shown here in this slide. We have corona, very well pronounced, and also microsparking taking place. Another type of EMI are gap discharges. Again, they're frequency selective. This picture was taken at 90 kilohertz. The pattern is not necessarily in synchronism with the power frequency. Much fewer discharges are present, as was with microsparking, because these are discharges taking place across relatively large gaps. The pattern is not as repetitious as microsparking because each discharge is actually chewing away the insulation or destroying the slot conductive paint on the stator bars. Another valuable tool of EMI monitoring is trend analysis of EMI activity over a particular period of time. The bottom dotted curve shows the spectrum of a pump generator taken in May. The upper darker line shows that same machine 6 months later. There was a dramatic increase in EMI at 100 kilohertz almost no increase in EMI levels 1 megahertz and above. This was an indication of slot discharges. As shown here, the discharges had bleached the center of the side packing, the non-conductive material used to hold the coils in the slot. As it progressed, the polymer that was holding the side packing together was dissolved, and then the glass fibers blown away by the breeze. Since EMI was tunable, I was quite curious at whether or not the resonant frequencies inherent to a machine would tell me where I could find EMI at. If you look at the impedance of one terminal of the machine, in this case 140 MVA turbine generator, you can see that that input impedance is quite dependent not only on frequency, but whether or not the opposite end of that circuit was open or shorted. In particular, at 19 kilohertz, the shorted line appeared to have a very high impedance of about 750 ohms. When the other end of that circuit was opened, it had a very low impedance. But this gives you somewhat of an idea that perhaps standing waves are occurring on the circuit in the machine. Likewise, on another machine at a higher frequency range, this time between 1 megahertz and 50 megahertz, you can see a cluster of frequencies of 2, 3, 4, 5, 6, 7, 8, and 9 megahertz, and a very sharp increase in impedance of 17 megahertz. In particular, those between 4 and 9 megahertz were also characteristics of standing waves. To help you understand the standing wave patterns that develop, I drew this. It shows that each stator bar could be either one complete cycle of an oscillation, or perhaps a half or a quarter or a third of an oscillation. The background for this work was done by Charles Proteus Steinmetz. In 1911, he published a series of lectures which describe what can happen on transmission lines at various frequencies. To paraphrase Steinmetz, a transmission line can be a resonant circuit if the section in oscillation is short when compared to the entire circuit length. If the section ends have the same electrical characteristics, that is, they're both open or they're both shorted, half-wave oscillations can occur. If, on the other hand, the section ends have opposite electrical characteristics, that is, one shorted and the other one open, then quarter wavelength oscillations can occur. To further clarify the Steinmetz criteria, he also noted that the velocity of propagation of a transient or electricity through a conductor changes with both the magnetic permeability and the dielectric constant of the surrounding media. In other words, some sort of correction factor needs to be made when you're not in free space. A cable, for example, has a velocity of about 1/2 that of an overhead transmission line. This is also true in stators between the slots and the end arms. By using the Steinmetz criteria, we can calculate what these frequencies might be in a generator stator by using some very simple equations. For example, if we say K is the velocity factor of the transmission of electricity through a particular media, it can be stated as the velocity difference between a conductor and that of free space, or K is equal to V over C. Likewise, to fit the Steinmetz criteria, if M were the number of slots per phase and S is the number of slots per half cycle, then M over S equal N, or that is, it must be an integral. You can't have a fraction of slots involved. For the one particular machine that I showed you a curve of earlier, the 36-slot 2Y machine, 907 MVA, there were 12 half coils per circuit. The velocity constant in the slot was 0.53, and the velocity constant in the end arm was 0.95. By using the previous equations and calculating out these frequencies, we can develop several frequencies that oscillations may occur. Also, with the Steinmetz criteria, he said that the section in oscillation must be short when compared to the entire circuit. So in other words, where 6 stator bars produce a half wave, or all 12 stator bars in a complete circuit produce a half wave, these oscillations may not occur. And indeed, if we refer back to the impedance curve, The lower frequency oscillations either do not exist or are very small, but we have very good correlation on the others. The calculated frequency of 4.4 megahertz was measured at 4.6. The calculated value of 5.9 was measured at 6. The calculated value of 8.8 megahertz turned out to be 9, and the calculated value of 17.6 megahertz was actually measured at 17. And indeed, when this machine did develop troubles with extreme contamination of water and rust on both of the end windings, one of the primary frequencies where the EMI occurred was at 17 megahertz. Obviously, another type of oscillation could take place within one stator bar instead of the entire stator circuit. In this case, the end arms and the slot sections can be reduced through the Steinmetz equations, where you can have 1 half cycle, 1 complete cycle, 3 half cycles, 4 half cycles, and on. And these can either be calculated or measured. In this case, this is the measured impedance of a single stator bar in the slot of a 140 MVA machine. In particular, the small hump at 25 megahertz is equal to 1 wavelength long. The area at 70.8 and 72 megahertz coincides with 3 wavelengths and 2.5 wavelengths. And of very great interest is at 128 megahertz, which is exactly 5 wavelengths long, where the impedance is 35,000 ohms. That drops to a value of 20 ohms at 139 megahertz, which is exactly 1/4 wavelength off 5 1/4 wavelengths. Another obvious resonance circuit is in the end arms themselves, where they exit the iron, go out to a connection, and then come back to the iron again. You can use the same type of formulas with a velocity constant of approximately 0.95 and calculate again a series of frequencies that you might find there. This indeed is the case of the 41.7 megahertz. As you saw in the earlier curve, we did have a small bump at 42 megahertz. One of the things that you noticeably measure at this frequency range is corona between the top and bottom bars. In this case, it shows up as a small white fungus-like growth where the top and bottom bars cross over each other. This particular machine had been in service for 30 years when this slide was taken. It's obviously not a harmful type of EMI. However, on modern machines with synthetic resin insulated bars, it may be detrimental. And of course, if you put all of these together, you can end up with a rather complex curve. In this case, this is the impedance of an entire circuit on the 140 MVA machine. It consists of 28 stator bars, 2 groups of 6, 2 groups of 8, and has well over a dozen resonant points between 10 megahertz and 300 megahertz. Each one of the resonant points indicates oscillation of a stator bar, end arms, phase rings, or combinations of those. The test equipment that we used were vacuum tube type oscillators. They were isolated from the part being tested, whether it was a stator bar in this case or the entire stator, with a resistor. Then the input voltage was held constant. We measured the voltage across the test piece with a demodulating probe and a digital voltmeter. The data was recorded and then converted to impedance. The other types of tests that were done were on the entire stators, where the signal generator was moved up underneath the machine and tests were made directly on the bushings. One of the problems encountered was trying to make a short circuit at 100 megahertz. Even though 2 twin conductors were used to try and ground the bar, the length of the ground itself was equivalent to a 1/4 wavelength, and only the open circuit test proved valuable results. To summarize, EMI is common to all machines. Certain defects generate EMI only at discrete frequencies. EMI frequencies can be extremely broad, in one particular machine from 6 kilohertz to 220 megahertz. Similar machines do produce a similar EMI spectra, depending on the stator design and the EMI present. EMI techniques have been proven applicable to steam turbine units from 125 megawatts single shaft to 1,300 megawatts cross compound units. It is also equally applicable to hydroelectric machines and will provide the maintenance engineer with data on making repairs before in-service failures occur.